So now I'm getting to the topic that I like to talk about, or like to teach the least, because I remember from when I learnt pointers, they're very confusing. Having them for some reason explained to you by someone that understands them is very confusing, and they're very hard to explain sometimes, even though at the heart of it, they're extremely simple. And once you understand it, you'll have like that eureka moment and it'll all make sense, and then all of a sudden C becomes the best programming language, because it is. So what are pointers? Pointers really are a reference to the memory location where something is stored. So we can remember that a variable is simply some data type size of bytes stored at some memory location. We reference where by using some identifier that's human readable, so we know, oh yeah, cool, this is my foo variable and this is my bar variable, because we don't care where they're stored in memory all the time, but it can be useful to say, to like, for instance, in a function when we don't want to have the function scope restricting us, be like, hey man, there's a variable over there at that memory location, can you modify it please? That would be great. And so we need a variable that stores these memory addresses. And so a pointer, all it is a value that stores, instead of the actual value of the variable, it stores the location at where the variable is stored in memory. So if we for instance have a variable called, we just say int foo equals 2, that means that somewhere the compiler will allocate a variable called foo, so it'll give 4 bytes and it will set those bytes equal to the value of 2. It will store 2. Where exactly in memory this thing lands, I mean, you can't really, I mean, it's just somewhat random to us as programmers, but we can take this memory location by using certain operators. For instance, here, this ampersand operator will take the memory address of this variable and store it in another variable. And this has benefits which we'll see in a minute. So you store a variable, you store the memory location in a variable, and we denote that it's a pointer by using this asterisk. So for instance, when I'm defining an integer, you would get rid of this asterisk here. This wouldn't be here, it would just be int foo. But if I want to say, hey, I am now pointing to a memory location where an integer is stored, I have int star. So int star is an integer pointer. And this is useful because all memory locations are the same size, right? Like they're all some 64-bit number on a 64-bit system that reference a memory location. How does your compiler know what is at that memory location? This is by the data type, or the type of pointer you're using. If it's an int pointer, the compiler knows I need to go to that memory location and get 4 bytes, right? So this is exactly what this point says here. And this ampersand operator is what we use to actually get the memory location of a variable. So I've created int foo. Now I want to store the location of it in like int star bar. I would say other way around. Let's say I want to store the location, I have int bar and I've got it somewhere in memory, and now I want to store a reference. I want to store its memory location in another variable, in an int pointer. You'd say int star foo. So I'm saying create an integer pointer with the name of foo, and here with the ampersand, store the location or the memory address of the bar variable in foo. Okay? Now, once we have, for instance here, we now have an int pointer foo, and in there is stored a 64-bit memory address. But like, how do we use this? We have this accessor, the star, the star operator, and what the star operator with a pointer does, it says, okay, you're storing a memory address. Let's go to that memory address and get what's there. And you know what's there because it's an int pointer, so you're saying, okay, cool, you're storing a memory address, you're an integer pointer, let's go to your memory address and get the integer. And so that's what this star does. It goes to the memory address stored in the pointer, right? And so this is the same for reads and writes. If you want to write to the memory address, you go like foo, you'd go foo star, and then and then you would set the, or you star foo. It's actually this way around, so you get rid of the int, star foo, and then you would set the value, or you would for reading it's the same thing. It's just star foo. Like it's the same as when you're using arrays. You just use the little square indice things, accesses to do both reads and writes, right? Exactly. Here's an example. So this is how you would tell essentially in this example, go into bar, which is stored in foo, and store 2 at that location, right? So I think pointers are very much best explained in examples. So hopefully, if you're not totally confused already, this will hopefully either confuse you more or help to clear things up a bit. So what we're doing in this first line with foo equals 2 is we're just creating a standard variable. This is going to be created on the stack because it's just statically declared. It's going to become the stack of main, the function, but it's going to be somewhere in memory. There is no hard border between the stack and the heap that stops pointers being able to get references. You can reference all of memory that your operating system or hardware lets you access. So here we're just creating a standard variable. If we print this, we'll just see 2. So because it's just a standard integer variable which has some value stored in it. Now, what we're doing here is we're defining an integer pointer called bar. And so the type of this is just an integer pointer. So we know that a memory address will be stored in it on a 64-bit system. This means that it'll be a 64-bit value. And we know that at the location of whatever it's storing, we will have an integer. So you have char pointers, int pointers, struct pointers, double pointers, float pointers, any data type you have as a pointer as well. The data type is literally just telling you how many bytes are at that memory address to be accessed, right? What we're doing on this line here is we're actually saying, okay, cool, we now have our integer pointer. Let's store the location of foo in it. So it's using the ampersand foo. It will go and find the memory address of foo and store the 64-bit memory address in bar. So if we now print foo, or print the memory address of foo, we'll see here that this is the memory address. It's a 64-bit value. And if we now print bar, we'll see the same thing, because bar is now storing the 64-bit value that is foo's memory address. On this last line, or these last couple of lines here, what we're doing is we know that foo is equal to 2. But by using this ampersand bar, we're saying, hey, bar stores the address of foo. Let's go to that memory address where we know an integer is stored, and let's put 4 there. And so what this is actually doing is overwriting foo equals 2 with foo equals 4. So this, if we then print foo, we'll see that foo now is equal to 4, even though we didn't directly modify foo. Like we didn't say foo equals 4. What we did instead was we took the memory address, which was stored in bar. We used this asterisk operator to go to that memory address where we knew an integer was stored, and we replaced the integer there with the value 4. And so that's what a pointer does. And why this is really, really useful is that I was talking about functions and how when you pass in a variable to a function as a parameter to a function, it's copied into the scope of the variable of the function, and when the function returns, the stack is destroyed and this variable doesn't exist anymore. So if you were to take the memory address of a variable and pass that in, so you just take a copy of the address. So you don't actually care if the address, so you take a copy of the address, and then you can actually say, okay, go to that address and store something. But when you return, the copy of the address is destroyed, but not is what is at the address. And so this means that whatever you do to a pointer directly in memory is still valid after a function returns. And so this is what these couple of points are saying. When you modify a pointer, you're modifying it directly in a heap. And because pointers are used to reference dynamically allocated variables, they can be used for statically allocated variables. But generally you use them with dynamically, so heap stuff that doesn't have a scope. Yeah? And so when you want to allocate memory on the heap, you use these alloc functions, and they return pointers because they're essentially allocating some block of memory of some sort of type, and it's up to you as a programmer to say, yep, cool, when I use this malloc, I'm allocating this size of memory. So in this case, it'll be 40 bytes. And I want to say, yep, it's an integer. So this makes, like in this case, there would probably be an array because you're allocating 10 integers, and you reference it by just taking the first one, like the address at the beginning, because then you know that the rest of them are sequential in memory, right? So this brings us on to memory management. Because these sort of go hand in hand.